Hi everyone, welcome back to the Materials for Energy and Sustainability workshop. Today we have two speakers, Professor Miguel Alario Franco, that will be talking about superconductors, and Dr. Beatriz Molero Sanchez, that will tell us about solid oxide fuel cells. The first speaker is Professor Miguel Alario Franco. I believe it is fair to say that Professor Alario is one of the main solid-state chemists in Spain, especially in the superconductivity field. He was former dean of the chemistry faculty of the Complutense University of Madrid between 1986 and 1994, and president of the Spanish Royal Academy of Science between 2009 and 2012. He was the founder and first president of the solid-state chemistry group of the Royal Spanish Chemistry Society, and currently he is member of the European Academy of Science. He has a PhD in chemical science and completed his postdoctoral studies in England, Wales, and Italy. He has been a visiting professor in Cambridge, Grenoble, Berkeley, and San Diego. And on his wide scientific career, he has obtained multiple prizes, but I would like to remark the prize of the Spanish Royal Academy of Science in 1988, Premio Rey Jaime I in Material Science in 1991, Premio México de Ciencia y Tecnología in 2009, and the Research Prize of the Comunidad of Madrid, Miguel Catalán, in 2011. He is co-author of a superconductivity book and editor of For Others. He is a member of the editorial board of 5 international scientific journals and a jury member of the prizes Príncipe de Asturias, DuPont, Solvay, Ramón y Cajal, and Rey Juan Carlos. He has supervised more than 25 PhD works and published more than 350 articles. Among his past students, there are 40 university full professors and several research scientists, both in Spain and abroad. Currently, he is enjoying a well-deserved position as honorary professor of inorganic chemistry at Complutense University of Madrid. So thank you, Miguel Ángel, for coming. It is a pleasure having you today.
Yeah. Thank you. Thank you very much, Elena. It's a very, very kind of you to say all good things. You didn't say any of the bad ones, so I'm grateful. Anyway, I'm going to talk to you today about the high-temperature superconductors from mercury through cuprates to hydrides, and I'll try to do a kind of a mix between a historical account and then some detailed results, some of which will be from our own group, but mostly to describe since the origin of superconductivity to the present day, which is a very active field indeed. In fact, before I start, I would like to dedicate this talk to Professor Emilio Morán Miguel, that many of you know, and he was my very best friend. I met him in 1974 as a student in the Autonomous University, and then we got together very well. We did a lot of work in research and also in just friends in family terms, and we established, the high-pressure lab, the hydrothermal synthesis lab. He was my great companion, and I am really very, very sorry for his disappearance in the pandemic. So I dedicate to Emilio this work, and then, things happen that are difficult to prevent. Anyway, so when I start giving a talk, a general kind, not in every lecture, I just ask Google if the thing I'm talking about is or is not important. And Google, who my friend Ivan Schuller, Professor Schuller from San Diego, says that Google is like God because he knows everything and he's everywhere. Well, not arriving to that much. I asked Google about the importance of the things we are doing. So let's say what it says about superconductivity. There are near 4 million results. Superconducting cuprates, about 1 million results. Superconductivity and high pressure, which is instrumental in the latest work on the field, 500,000. Superconducting hydrides, which are the stars at the present time in many laboratories of superconductivity, about 1/3 room temperature superconductivity is really very, very interesting because more than 5 million results in half a second, in half a minute or a third of a minute. And then superconductivity predictions, which is an unusual thing, but you will see that there have been many predictions along history, and most of them, if not all, were wrong. I will talk a little bit about predictions later on. So let's start with superconductivity, which is a property that some materials have for conducting electricity without energy loss, so without resistance, without Joule effect, below a certain temperature, which is critical, is called the critical temperature, which is a critical parameter. These materials also have another property, which is even more important, if I may say, which is that they expel the magnetic field when they are in the superconducting state. Before I actually enter in the science, let's see some of the applications, because superconductivity is something which is helping people to do things that cannot be done otherwise. For example, well, everybody knows this levitation. As they expel the magnetic field, you can actually levitate a pellet of a superconductor below the critical temperature. This is a typical experiment that we do in schools and divulgation for people. But then in the applications, we have, for example, superconducting magnetic energy storage. This is a system in which, because there is no resistance, you can actually drive in a current and keep it in there while you are below the critical temperature, and you can store the electrical energy, and whenever you need it, you just take it out. So you can have it for an infinite or almost infinite time, turning around a coil, and this coil is cool. This is why it's so spectacular and big. This is something one can actually buy in a firm called American Superconductors. Another very exceptional thing is this magnet, which is actually a detector at CERN, which is the European Laboratory for Particle Physics. And this is probably the biggest instrument that has ever been built by humanity. Well, there are here 8 toroidal superconducting magnets that surround this detector, which is the Atlas detector, where they study hitting protons with protons and then study the particles which are produced. It is an immense instrument, and you can notice the size by looking at the person that was actually the director of the installation, which is really a job that of certain importance. Look at the size of the man and the size of the instrument. So that's thanks to superconductivity. A much more common thing is the nuclear magnetic resonance spectrometers, which in this case are applied to our making images. Here we have on the left a very recent equipment, which is for the body. You can actually put the body in. And then on the right, we have one of these images that you can make a much higher resolution than X-ray, and also is not dangerous. I mean, you don't have any damage for being in the NMR, although it normally makes a lot of noise. I'm not into this, and people get afraid, but in fact, it's absolutely innocuous. It doesn't make any problem. And finally, perhaps the most or better known or more talked about is the high-speed levitation trains. This is a model which is being developed in Japan. China is also developing. Just 2 days ago, it was published in the press that they have designed a new one that will be able to get 600 kilometers an hour. There is one in China already, but it's a German train that flies, because it's actually flying, from Shanghai to Shanghai Airport, which I have taken, and there you can get at 400 kilometers an hour. This is thanks to levitation and also to the way that you can, the propulsion is also based in magnetic effect of superconductors. So it's really something, superconductivity, that's contributed a lot to, let's say, civilization in a general term. Now, another way of saying if something is important in science, and in particular in physics and chemistry, so is to measure or to see the number of Nobel Prizes that have been attributed to superconductivity. And this is a really big number. First one is Cameron-Ons, which was the discoverer of superconductivity in mercury in 19-something, 1905 or 1906. And then you see here, and see later on a little more, the resistivity of mercury disappears at 4.2. The second group of Nobel Prizes was given to Bardeen, Cooper, and Schrieffer. Bardeen had already a Nobel Prize for the discovery of the transistor earlier than that, almost 15 years before. And the idea that gave him this theory is that for superconductivity, you have electron pairs, which are called the Cooper pairs. Cooper is the fellow in the middle. And this, when one electron goes through in the superconductor states, goes along the lattice, well, then it produces a distortion, a polarization of the lattice, and this distortion attracts the other electron. So at the end, it's like if you had two electrons moving, and then the mathematical model for describing this phenomenon, which actually is a quantum phenomenon, rather complex, but still can be explained with this theory. That is then the theory of superconductivity. And in the University of Illinois, there is a display which commemorates the date in which this discovery was made. Well, the moment in which it was known. Later on, Josephson and Yauk, this gentleman working in something else, Josephson discovered in his PhD, so he was a very, very early scientist, became infamous. He discovered the Josephson effect, which is when you put two superconductors with an insulator in the middle, and then you have the current can go through. And this is very important, as we will see later on. Well, there was a gap between these two dates, and in 1987, Benders and Müller, working in a famous physicist and a modest chemist, working in Zurich in IBM, discovered high TC superconductors based in copper oxides. And finally, in 2003, Abrikosov, Ginzburg were also given a Nobel Prize in physics for a work in superconductivity. We're going to give details in a moment. And then Leggett, who is a British physicist, he was given this 1/3 of the prize or half of the prize because of his work in superfluidity, which is a very similar phenomenon to superconductivity, but for fluids instead of for electrons. So these are the official Nobel Prizes for superconductivity. But I believe that there are 3 more people which deserve to be named when you talk about superconductivity. First one is Lev Landau, who was probably the most important physicist of the Soviet Union, probably of all times. And he actually published books, and he was the thesis director of both Abrikosov and Ginzburg, and he was really an extraordinary physicist, and he made big contributions to superconductivity, although he was given the Nobel Prize, but for his general contribution to physics. Then another one is Phil Anderson, who was a very interesting person, very looking more an English than an American, and he was given his prize for metal insulator transitions at the same time as Sir Neville Mott. And by then he hadn't worked on superconductivity, but after the discovery of superconducting cuprates, he has done interesting contributions based in so-called resonance variable bond. And then finally, in this area, Pierre-Gilles Degennes, a French scientist, very, very important in physics, and in particular at the beginning in superconductivity. But in the 70s, he thought that late 70s, he thought that superconductivity was already finished. So he actually decided to stop working on that because he said that, well, a semiconductor you can control, a superconductor you don't know when something is going to be superconductor. So he left the field and he worked in other things related to gels and their nature. But he has a book which is a classic in superconductivity, which everybody should read. Okay, so these are the famous people the most famous people on superconductivity. Ginsburg in particular, I'll mention a little more because, well, it's a person, I never met him, but I liked him very much. I invited him to come to the Spanish Escorial courses in the summer, and Abrikosov did come. He says he will not be given a visa, so he didn't attempt, but Abrikosov could come. Well, Ginsburg has made big contributions to physics, and considering superconductivity, he has one of the predictions that one could get actually up to 300 Kelvin for a material in normal conditions. So in the absence of pressure, that would be the limit in his opinion. But on the other hand, he said that at the present, in the time that was in the 2000 something, the problem had the most fruitful approach would be the one that is not preconceived. So you just look around and fish, and then to move in most diverse directions. So in fact, here he says that just to go and work. Then he's also famous for having done the so-called Ginsburg list of famous problems in physics. Control nuclear fusion, which is a very interesting subject in which superconductivity has a lot to do. Then high temperature superconductivity and room temperature and metallic hydrogen. These were the three most important problems in physics. There is up to 10 different problems. Okay, well, then now that we know what is the superconductivity for, what is you can reuse, then who are the people that has contributed more? Let's start back to science and to see electricity on a solid, on a metal. What is the resistance of a metal at room temperature? So, well, at room temperature, we have copper, which is a very good metal, aluminum also. Then lead and mercury are poor metals at room temperature, and they are not superconductors. This mercury and IPCO, this is already a cuprate, these are poor metals but became superconductors in different conditions. Then we have insulators, diamond, which is a semiconductor with a very, very big band gap. So is copper oxide. And then a typical insulator like quartz, where it has a very, very high resistivity. So we go from copper, which is in micro-ohms, to an insulator which is 10 to the 24, which means that resistivity is a property, but that's the copper resistance. And resistivity spans 25 orders of magnitude, which is a very wide margin. It's not the same to measure this resistivity than to measure this resistivity. You need a different instrument even. Anyway, we have copper resistivity here, or resistance, and then you see that if you cool down, resistance goes down, and then it stops. This is how we know now that we can get these temperatures. And then at the beginning of the end of the 19th century, Dewar was very famous in low temperature physics, and it was probably everybody knows the Dewar flask. We still use to keep nitrogen, for example. He studied the resistivity of mercury, and you see a beautiful phase transition from a liquid mercury to solid mercury, which takes place at 200 or something. And then he extrapolated down. He saw that if he could cool down, that would go down to zero. So that at the time, there was, in fact, three models of the value of the evolution of the resistivity of a metal as a function of temperature. It was the model of Dewar that we have just mentioned, heat. The model of Kelvin. Kelvin thought that actually the electron will be stopping when you cool, and finally they will probably not move, and then the resistivity will increase. And then there was the model of Mathiesen, who is not so well known well, not in the general public, certainly it is so in physics, he is so in physics, and he thought that the resistivity will attain a fixed value, which value will depend on the purity of the material. And in fact, in the work of Cameron-Reynolds, which we can show here now, yes, then this is the work of Cameron-Reynolds in wires of different metals. He noticed Cameron-Reynolds, once he was able to cool, to make liquid helium, which was a very difficult problem, we'll see the equipment in a moment, he decided to measure the properties of metals at so low temperatures. And you can see that this is platinum and this is also platinum, but purified. And then you see that depending on the purity, the material has a lower cut of the ordinate origin, which is the resistivity. So the resistivity always ends up somewhere, and this somewhere depends on the purity of the material. So it doesn't really get to zero in experimental terms. And then, yes, then the discovery of superconductivity was done by Cameron-Reynolds. It was his technician, film, and then this is the big equipment, which is a big compressor. You need a very big machine to compress the helium, and this is done in cryostat, which is a mixture of glass, metals and wires, and really a very, very complicated equipment, plus all the machinery that make compressions and expansions of the gas. So with this, he actually was able to measure what we said, the resistivity of several metals, and you see that mercury already shows pretty well that is different, well, different of the others. You can see it goes down, and then we have this little bit here that if we can get it in big, so the resistivity actually disappears. So in his notebook, he mentioned quick nanenognul, okay, which means that the mercury resistance becomes practically zero. So this is when discovery was, the superconductivity was discovered, and then he actually invented the word, and then well, became a very interesting person in science and in the history of science. This is really a remarkable discovery. We have talked mostly about resistivity, but in fact the magnetic properties of a superconductor are as important, because there's no point in saying more important or less important, as important. So in a normal material, magnetic field can go through. If you have a superconductor, it expels the magnetic field. In fact, that means you can have two types of superconductors. One is that you increase the field and suddenly it enters the material, and then when it saturates. And another type of materials, you go slowly, and then it increases partially, and then when you get down, it doesn't get out completely. So there is some magnetic stuff which stays into the material. That doesn't happen in here. So in fact, we have two types of superconductors. Type 1 is this one, superconducting state or normal state. In the other one, which is a type 2, we have superconducting state, then normal, but in the middle is a mixture, which is a mixture of normal and superconducting regions, as you can see here. And this is produced, these magnetic field lines get in the shape of vortices. And a vortex is the same thing that you get on a sink when you get a liquid through a sink, or things that you get in the atmosphere when a plane is flying. And then, so you see that this is in an airfield, and you can see that when the plane goes, you get a very big vortex here. This is the reason why two planes cannot get actually too close, because then one will be down because of the vortex that the other generates. Alexei Abrikosov, that I saw you before, a student of Landau, imagined that this vortex will not be disordered, that there will be actually order, and the bigger the field, the bigger the number of vortices. And then, he even established that it should be an hexagonal lattice, and he showed this to Landau. And Landau, he had And then, incidentally, he was 19 years old when he actually discovered this. He's one of the cleverest persons in the history of physics. And he showed to Landau, and Landau say, "Oh, that's interesting, but well, we are not going to pass the thesis yet. It's a bit early. Let's wait. And 2 years later, Leggett and others found in helium superfluidity, and it's the same idea. You have vortex of the fluid, and then when Landau showed the vortex in helium, in liquid helium, he said, "Oh, that's the idea of Fabricus. Said, now we can pass our thesis." So it could have been doctored 2 years before. Anyway, Fabricus showed that the vortex should be ordered, and this is the first picture of the vortex of a superconductor, which I think is titanium selenide, and you see that it's a perfectly ordered hexagonal lattice, but this can be more elaborate. So the phase diagram of a superconductor is complicated. You can have a superconducting state, the flux is expelled. Then here we have a mixer that can be ordered or disordered, and then you go to this normal state. So it's a beautiful phase diagram, and it can be really very complicated. This is the phase diagram of these materials only in terms of superconductivity. So you have hexagonal, rhombic, square, hexagonal, normal, and all this superconductivity. So it's a very interesting phenomenon. How common is superconductivity? Well, in fact, it's very, very common. There are many materials which are superconductors of different types. Here you have, well, I will not describe, but you have many, many things which are superconductors. It's just a small list. So superconductivity is a relatively common phenomenon that takes place in a great variety of materials. I haven't included here cuprates. I will talk about that in just a moment. So from now, I will make a chronology, the history of the discovery of superconductors. So we start from mercury to germanium, and maximum TC is 23. Then the first intermission, and not much research here. Then high TC superconductors, and TC gets much higher. Second period with little things, a few, but not many, and not very interesting. Then pnictides, another period. TC is not very high, but interesting material. Then fourth act, we arrive to room temperature, but in a transient mode, so only very, very briefly. You can get room temperature, but very briefly. And then, which is now where we are now, we can get to room temperature and ahead of room temperature, but under very high pressure. So that would be the fifth thing. So at the beginning, excuse me. At the beginning, well, of course, it was the metallic element. So you have here mercury, lead, niobium. Here we have temperatures, and here we have the year. So the elemental superconductors, here we have a plot of symmetry. Was the temperatures were more or less increasing, but this is without pressure, and this is with pressure. In fact, a more general table is this, which is called periodic table of superconductivity, but as you can see, it's not a periodic table because there is no periodicity. In fact, we have 30 materials which are superconductors at room pressure, and 23 which are superconductors only under pressure. And in fact, it is not a periodic property. So it doesn't depend on the electron configuration, as all periodic properties depend. So, well, but first the elements, then oxides and nitrides, the simplest one, NBO, nitrogen, NBN, which has a sodium chloride structure. Then an important discovery was the A15 structure, which was found in another area, but in fact, many materials with this structure are superconductors. And in fact, we have a whole list here of materials. All of these have the same structure, which is also called beta silicium structure, but it was actually an impure silicon that had it. And then, so these materials are very important. Most applications so far have been done with these materials, which besides having critical temperatures, which are relatively high, this is over hydrogen already, so you can actually use it for with hydrogen or with helium. These are quite high critical temperatures, but you also have critical fields. So these materials sustain a pretty big magnetic field, so you can do applications like the ones I've shown you before. So that was the A15 structure. This is due mainly to another person very important in the history of superconductivity, which is Bernd Matthias. He was working in San Diego and he prepared over 30 of these materials. And in fact, the maximum TC was 18 Kelvin, but there are others, as you have seen later on. And then, as everybody working in superconductivity, he liked to make predictions and make rules. Transition metals are better than normal metals. Density of states at the Fermi is good. Better cubic than orthogonal, than rhombohedral. And then two predictions which are interesting. Stay away from oxygen, magnetism, and insulated phases. And also stay away from theories. That, I think, is very funny. Anyway, that is Matthias' rule. But he also discovered a new class of combining ferromagnet and semiconductors. Very interesting science indeed. You can read a biography, very nice, very interesting biography of Bernd Matthias in Physica B in 2001 by Theo Gibol, who's one of his students. That is also, he was still active 2 years ago. He's 95 now, if I am not wrong. Anyway, the next, more on the Matthias era is that they made a review of the work that has been done at his time. Then he said that in this review, physical review, he says oxides and hydrides will be omitted from the present review since they are not important. So he made a prediction. But predictions are mostly very often wrong. Niels Bohr, who is another giant of science, particular physics and chemistry, say that predictions are very difficult to do, especially if they refer to the future. Now, of course, predictions to the past are very easy to do. Anyway, we keep on going, and then from 1940 to 1970, the slope of the plot is about 3 degrees every 10 years, which is, of course, very, very small slope, very low. So where will we get to room temperature, which is important for applications? Then, well, in that time, in 1970, somebody, I forgot the name, suggested that TC, by an extrapolation, suggested that we will reach room temperature superconductivity in 2840, which is a very, very funny. It is not good for the people working in the field. Anyway, always that you made predictions, often you are wrong. For example, oxides are superconductors. This is an interesting one. And the critical temperature is very low. It's interesting that it changes with the oxygen composition. This is the first material in which I worked on superconductivity in the 70s, just after I arrived from England. And it's a very interesting. Now the critical temperature is very low. But then, in that time, an spinel was found, this interesting compound, with 13 Kelvin, and a perovskite, another perovskite, also same. So in this period, two more materials were found. They're not very high temperature, but two interesting structures. So spinel is very well known, and perovskite even more. It's the most important structure in solid state physics and chemistry. Anyway, so Matthias was out of register with the reality. The predictions are difficult. So we should not make many predictions. Then there is a period in which not that many things happen. And then superconductivity, high temperature superconductivity appears. Then we have Balakwa. This is, I normally say in this, when we arrive to this point, that when you, in the 18th century, when there was a lot of nautic travel, the ships going to America or to Asia, and the trading was very important, people say that they should arrive to a point that there will be no more linen on Earth that you could make sails of. So it's traveling by boat, by sailing boats, by sailing ships will be stopped. And then the machine, the vapor machine, the Watt discovered, and so the ships now don't go just with an engine. So when we make a prediction, normally something happens that changes. In this particular case of superconductivity, it was the discovery of this material, which is an oxide, and that has a structure related to perovskite. You can see here that the temperatures, the critical temperatures, are much higher. So besides, after this, a lot of people started to work on superconductivity because these materials were relatively simpler than all the ones we've seen before. And that's the article that took them to the Nobel Prize, as we mentioned before. And then immediately, chemists in particular started to make substitutions. So the first substitution was barium by strontium, something we call chemical pressure. But then other people did actually mechanical pressure. And both things increased superconductivity. And a little later, the IPCO appeared. IPCO is very similar to Balakwo, and is based on the perovskite structure. You see here is a perovskite, but you have some oxygens missing. This is why it is O7 and it's not O9 that should be. But anyway, perovskite-based materials were the clue for the cuprates. I open a parenthesis just to show you the first superconductor made in Spain, because it was an interesting thing for us, for the group, and also because Emilio was very much involved. We co-directed the thesis of Flaviano García Alvarado, and preparing this material that you see is a perfect plot of resistivity for a superconductor, and the temperature at the time was the record, the highest TC measure so far. And this is, so Emilio, as you see, is always present in our work in this thing. This is the simplest model of the structure we are going to use from now on. It's a perovskite, well, most of it, but some, the unit cell. You have a strontium, barium, yttrium, barium. This is oxygen, and these are the oxygen, and these are the copper. So IPCO, if we continue as chemists do, making substitutions, bismuth, thallium, mercury. So we have a very, very low slope, and then suddenly, boom, almost vertical. We got these fantastic materials, and then the maximum, which is still the one, is 138 Kelvin at the room pressure. But if you put high pressure, you can go to 165 under 25 gigapascal. That's a huge pressure. But you see, this indicates that pressure can be very good in improving critical temperature and superconducting properties. And this is what is happening at the present time, as we are going to see in just a moment. So this is the result of the discovery of barium, lanthanum, copper. All these are enormous things. So it's like the linen for the sails in the boats. Now, we did some work on this replacements, and we got the highest TC for a non-toxic material, because mercury and thallium and bismuth are all toxic. Well, bismuth not, but, and also under pressure, we got very high temperature, critical temperatures at 136. But these materials are very difficult to make and rather not very pure. We made a patent, but well, it wasn't very useful. Anyway, it's big data. Anyway, so after the high TC superconductors, we have another period in which very little it was done, but very little doesn't mean anything. I mean, something was done. For example, magnesium boride, I talk to you in a moment. So there we have already divided this into two. These are conventional superconductors. These are so-called heavy fermions. I cannot go today, but this, you can use BCS theory. Here you cannot use BCS theory. And well, of these materials, magnesium boride was just bought. It taken 100. It was rather expensive, but it was a superconductor. Nobody expected that, and Akimitsu in Japan just decided one day, for reasons that are not clear, they measured the properties of this thing in the store, from the store, and it's really a superconductor, also at rather high temperatures. Which was really the record for materials which have not cuprates. And you have this one, which is also an interesting one, but much lower temperature. That was the previous record for this type of material. Another interesting thing, which I briefly mentioned, is the isotope effect, which is that if you change the mass of the atoms, you change the critical temperature, because in the theory, which I'm not going to explain, the critical temperature, this is Boltzmann constant, depends on the Debye frequency. And the Debye frequency depends on the mass. So if you diminish the mass, you increase W, and then you increase Tc. And you can see that here. That changes the mass of the boron isotope. This is another interesting mechanism in superconductivity. Anyway, another prediction. Magnetism and superconductivity are incompatible. However, there are materials like this, which is superconductor, and then if you cool down, reappear superconductivity. These particular materials then is so-called reentrant behavior. But another nicer thing to call it is Lazarus superconductivity. I'm sure all of you know in the Bible that Jesus is able to resuscitate Lazarus. And so here, as it reappears, this is called Lazarus superconductivity, a very funny denomination. Well, a similar coexistence of magnetism and superconductivity is in here. We have had several theses on this. The material can be both magnetic because of the electrode here and superconductor because of this part. So it's not incompatible, but not the same electrons. In one area is one thing, in the other one is another thing. We carry on, and then predictions are usually wrong, as I insist. Well, pnictides, not very interesting, because now they are superseded by others. These are halides, these are chalcogenides, these are pnictides. And then there is a big family of pnictides discovered by a good friend Hideo Osono. And then, these are similar materials to IPCO in the cuprate, in the sense that they are also layer structures. But the critical temperatures are much lower, and then they have arsenic and things which are not easy to use in industry. But also the critical temperatures are not very high, are rather low. There is an exception. Well, these are the phase diagram, which are very, very nice. And then this is selenium iron selenide, which has apparently a very high Tc, but this is a complicated material for some reasons. So after the pnictides, we get to the fourth act, in which we will see optical enhancement of Tc up to room temperature, but in a transient mode. So for this, we have to recall the spectrum of electromagnetic radiation, which is the terahertz region, microwaves. People here not work microwaves, infrared, visible. But it's interesting, this terahertz spectroscopy, excuse me, because you can actually be very precise in making pulses of terahertz spectroscopy of the terahertz region. And so 1 terahertz is about 4.1 milli-electron volt. That means that you can actually excite one single bond in a material. Well, signatures of superconductivity is electrical, magnetic, but we also have the possibility of studying the optical signature of superconductivity by a spectroscopy which is called PAM-PAM-PRO. You have the sample, and then you excite it with a pulse of terahertz region, and then once that you have excited the material, you send another beam in which you do the spectroscopy of the situation in the excited state. This is pulsed, so it's very, very brief. And then one can excite, as I say, a single bond in the structure. This excitation by the terahertz is called Josephson resonance. We'll see in a minute why is it called Josephson resonance. That will be the pulse. And then this is the resonance, the absorption. So this is the spectrum, and this came from here, and this came from here. Okay, so the interesting thing, this is the work of Cavalieri in Hamburg and in Cambridge. He's an Italian physicist that is professor in both Hamburg and Cambridge, which is most unusual. Well, besides doing the spectroscopy, they have done diffraction. They use the SLAC, which is a machine to do instantaneous X-ray diffraction, and this is in California. I cannot really describe, but here you can see that when you make this pulse, you get this absorption spectroscopy, but you also have an effect in the X-ray lines. Here we represent the variation of the intensity of the peak as a function of time. You see it increases, and then as the pulse disappears, it goes down. And they're in different X-ray lines. So two things you have to do. In the one hand, spectroscopy, and in the other hand, structural data in a very, very short time. So this is very difficult to do, but it has been done. So let's go to the Josephson junction. If we recall this model I just mentioned here, we put two of these unit cells, and then we have here a superconducting bilayer, an insulating layer, and another superconducting bilayer. And so this is the charge reservoir, this is the charge reservoir in the IPCO. So that will be this, and this will be this. So we get a superconductor, an insulator, a superconductor. So this is a Josephson junction, which is the thing that actually gives this Josephson resonance. So the electrons can actually travel. You can see that better in the original drawing of Cavalieri's group. So that will be the superconducting bilayer here, and this is the other one, and this is the insulator. So that's the Josephson junction. So in normal circumstances, there is no connection between here. Very little, even if you put an electron current here, it doesn't go, or it doesn't superconduct. But then if you make the pulse, then things change. So you said 300 femtoseconds, very, very brief. So what happens then? You get change in the structure. This change in the structure is the following. This is the same as we have seen before. So this, which is the bilayer, increases, and this, which is the interlayer, decreases. So it means that you are transferring current from here to here. So this is less strong, and this is more strong. So, in fact, if you measure now with the X-ray diffraction, this machine in California, then you see that the intrabilayer goes up and the interbilayer goes down. So this increases and this decreases. Well, this we represent this in the structure. This is a cartoon that I made myself. When you send the pulse and the excitation go to here, what you have is you get these oxygens get close to the copper here. And this is called the apical distance is the crucial bond that you can actually change when you send a pulse of the terahertz spectroscopy. Okay, and then as it is very brief, when there is a de-excitation, and then the atoms go to the original position. So in that brief moment, you have superconductivity, and at the end, as you can see, the distance will go back to the origin. So it's a transient process. We get superconductivity, but in a very brief time. Now, the phase diagram that they have done with many studies, the people of Cavalieri, is that you have the whole concentration that depends on the oxygen content, and this is the critical temperature, and thanks to these pulses, you can actually, depending on the oxygen content of the stuff, you get a TC, which is here is 150, 350, so quite higher than room temperature. But as I say, and it's very important, is that you only, is very brief, and also you cannot get much phase superconductivity. If we suppose that this is the material, we only have about 10% of regions which became superconducting and back to non-superconducting. So every pulse you get it. So we have tried to emulate this in the work of Susana Lopez and Xavier Martinez de Irujo, and we have been able to, by oxidation, instead of using a pulse, we like to make it a permanent thing. So we use the chemical reaction. So we use ozone oxidation of this material, and then, well, we get the apical distance. You see that it decreases. The interbilayer decreases and the intrabilayer increases. So exactly the same as before. And we observe indeed that TC, this is the normal one, simply with oxygen, with ozone, the TC increases, and with high pressure, high oxygen pressure, we increase. So this is a permanent phenomenon. With oxidation, the apical distance decreases and TC increases. But it's a permanent effect, but the amount of the temperature that we achieve is very low compared with what they do. So we have to work more. I mean, it's a long story, this. It will be too long for me to explain all this. Anyway, so we arrived to the end of the thing, which is, I hope you still haven't got asleep because of the timing of the lecture, but I'm just finishing. We go to the hydrides, hydrogen hydrides, which is the most relevant at the present time. There are many laboratories working on this, but it's always based in predictions. John Bernal, a very famous communist Irish scientist working in England, it said that all materials will be made metallic at high pressures. Then Wigner, or another famous physicist, they said that at 0 Kelvin and hydrogen will be metallic. It will be like a network of protons with localized electrons. A very useful idea, in fact. Then Abrikosov, the one that I mentioned for the vortex, he said that the coupling mechanism must increase under pressure. So pressure will be favorable of getting the copper pairs. Then Ashcroft said that metallic hydrogen might be superconductor due to stronger electron-phonon coupling, as I mentioned before. And then metallic hydrogen has been considered the holy grail of high-pressure physics. I'm sure you know that the holy grail is supposed to be the cup on the Last Supper by Jesus. You see, Bible and physics are quite mixed up in superconductivity. Anyway, it's complicated, this story of hydrogen is metallic. The first experiments were done in Livermore National Laboratory. I've been there when I was in Berkeley. And then you have a gun. This is like a gun, like a fusil. And then you put here a powder bag, and this is a piston. You have here a gas. It doesn't need to be hydrogen. The hydrogen that we are going to make metallic is in the target, not in here. So when you ignite this, there's an explosion, and the piston compresses the gas in here, and then you have here an impactor, and the impactor runs around the gun, the barrel to the target. And then, so at the beginning is like this, then the hot gases pushes. How is and that's the target. So the target is in fact composed of two alumina crystals, and we have hydrogen in between. And then you have a series of connections to measure the resistivity. So this impactor is this one that actually touches here at very, very high speed. So if you measure the resistivity of the target as a function of the pressure, and the pressure depends on the amount of powder that you put here, you see that the resistivity diminishes, and then finally is very low and constant. So you get a process of metallization. That's the first experiment back in 1996. I also know Nellis, and he was very proud, but not everybody believed this experiment. Anyway, this is metallization. Now, more recently, there is a lot of work on this. This article by Philip Bohr is very nice because he describes the good things about this, which they are not really clear evidence. But very, very recently, there is a group in France that working at no less than 425 gigapascals, and in a synchrotron have found probably a metallic hydrogen. This is the work. This is done in a diamond anvil set. You have two diamonds here, and then when you put the hydrogen, something which is not very simple, and you make pressure by pressing these screws. You make the diamonds get together. Then here is 350 gigapascals going up, 300 going down, and this is the maximum pressure, which is 427 gigapascal. You can actually see the change in the color, and this here is practically transparent. This is the metallic state. So this is one proof that the hydrogen is probably metallic, but they also have done spectroscopy. So you can do X-ray and spectroscopy. Because diamonds are transparent to X-rays, but you can also do spectra. And then the spectra indicate here a series of peaks, which is due to the vibrons. Vibrons is like phonons, but it's vibrations, quantum vibrations of the lattice. And also, and this is the most important one, this is the diamond band gap. And as you can see, in a certain pressure, the highest pressure, the diamond gap closes. So the diamond, the hydrogen, the hydrogen band gap here is what this an insulator is already a solid, but an insulator here they actually close the band gap, and also it becomes a metal. So probably metallic hydrogen has existed. Well, is that useful for something? Well, it's useful for knowledge. We have here the solar system and Jupiter. Jupiter is the most important planet because it's very big. And the interesting thing is that inside we have hydrogen. And with such a big mass, we have a tremendous gravitation. So, in fact, we have high pressure, and it is presumed that we have solid hydrogen in here. The solid hydrogen, which is because the planet is rotating, generates a magnetic field. And this is Jupiter's magnetic field due to the presence of solid hydrogen here, of a metal. And this is believed to be is the biggest object in the solar system, except, of course, the solar atmosphere in the solar itself. But this is the biggest object. So we can understand why Jupiter has a magnetic field because of the presence of hydrogen, solid hydrogen. Well, hydrides have been approached in different ways. I will accelerate a little bit just to show the latest data. Some metallic hydrides were long ago, but the superconductivity was very low, not very interesting. Until again, these are if you have done inorganic chemistry, you probably have learned this very clearly. This is the water, and then you have here the boiling points and the hydrogen bond, and so. But so there are many, many hydrides, and the idea is that hydrogen. It was very difficult to make it metallic. What if instead of hydrogen we use a hydride? And then the first hydride that haven't actually given the good result are this, selenium and sulfur. So, first of all, there were some people that did calculations in dense hydrogen sulfide. And then Elements and his group in Germany did experiments, and they actually obtained, this is the different structures of sulfur dihydride, sulfuric acid when it's in water. It is not molecular species, but these are the different structures. This is the one that is believed to be the superconductive one, and it's probably SH3, not SH2. But this is a record, the first big critical temperature. And then these are the data. You see that when you increase the pressure, you are increasing the critical temperature. And well, here, temperature as a function of pressure. And the interesting thing again is that this is with deuterium, so there is an isotope effect. So it means that these have Bardeen copper Schrieffer model. And then these are the magnetic measurements. Very difficult to do magnetic measurements at these very high pressures. So, well, here again, you see these are the contacts to make the measurements in the diamond anvil cell. These changes in color, you can do spectroscopy, and in fact, well, you can see how it changes the critical temperature with pressure. So it is clear that SH3 is a superconductor with a temperature above 200, but a very high pressure. Now we are in this region. We have this came out. This is in 2014. But then, again, it's conventional. Now, this is really two more slides, I think. This is the periodic table of binary hydride superconductors. This is the temperatures which have been calculated for this, the critical temperatures, and these are the experimental. You see the highest are this one, which has been experimentally confirmed, and this one, which hasn't yet been confirmed, although there are data. So there are two recent works. One is the lanthanum H10 and yttrium H10, and this will be the critical temperature. So yttrium will be the highest, and then experimental data, this is the lanthanum, which has been confirmed. This hasn't yet been measured. And this actually was presented in a meeting that I organized in the RSEQ Foundation. You can access to this book. If you look at the Foundation webpage and you look in books, you see it's Symposium in Pressure and Superconductivity. Hemley was there giving the talk. So at present, we will have this. We are in here. And so we started in mercury. We have been in cuprates. And then we are now over here, 260 Kelvin, but at a terribly high pressure. So in fact, yes. The last idea is this material, which is only known as a carbonaceous sulfur hydride because they have mixed it up sulfur hydride with something, carbon monoxide or something. And then, but this is not yet confirmed. And so we have to take that with a little care. So the present record is a compound with an unknown composition. But for a scientist, if it's an unknown composition, the data are not very, very important. So where do we go from here? Prediction. Should I do a prediction myself, which I'm just showing you that predictions are usually wrong? Well, we have serendipity. Emilio Moran used to tell us, to teach us that serendipity in Spanish is chiripa, and nobody had thought about that before. It's exactly chiripa that you may find new materials or new other things. Well, if we keep going with the last two examples I show you, chemical modifications to control and change interatomic distance, or trying to prepare hydrides of the big list that I have shown you, but not with lower pressure. That would be more interesting. So that's all I want to tell you. Thank you for your patience, and I believe I've been a bit longer, but I wanted to tell you all of this, so I thank you for your patience. Thank you.
Thank you so much for participating in this workshop, Professor Miguel, and for this interesting talk. If you don't mind, we are going to start with the questions. The first one, you have mentioned the Nobel Prizes who create the BCS theory. Could you please explain us a little that theory?
Excuse me, I didn't catch the question properly.
Okay. I repeat. You have mentioned the Nobel Prizes who create the BCS
Yes, but
theory.
in Complutense Refer, yes.
Could you please explain us a little that theory? A little bit.
Well, I can if I go to my first slide. So I will try to go to my first slide. I think that may be possible. Yes, it may be possible. ¿Cómo se hace esto? Sí. Yes. Here. Yes. Here. Let's see if he wants. Yes. Right. I think it's coming. One moment. Stop. Yes. Okay. Yes. See. Right. Well, here on this drawing, you have here, supposed to be atoms, hydrogen or whatever. But let's suppose atoms of a metal like that became superconductor like niobium, and then you put an electric current here. Before this starts to move, you put an electric potential here, then electrons move. Electrons, normally the classical description of a metal is that you have the positive ions forming a lattice, and then the electrons is like a fluid in there, and in the presence of an electric field, this C goes from the positive to from the negative to the positive size of the potential. So this is what happens in normal conditions. But in normal conditions, the electrons hit the atoms. So you produce there a phenomenon which is called the Joule heating, which is because the friction of the electrons and hitting one atom than another, the electron gets slow, and also the material gets hot. So you have resistance, electrical resistance. What happens in here, the cartoon is very simple. When you get one electron that goes through the lattice, then the lattice is affected because the negative charge of the electrons attracts the positive charge of the ions. And then this field that has created one electron attracts the other one. So at the end, you see, you can actually move in two electrons. And this moving of the two electrons is actually a quantum phenomenon. That's a little more complicated to discuss, but the idea is that when you put two electrons, they became in a quantum state in which they are actually resistivity, so they don't have resistivity. From this on, things became much more complicated. I show you a formula in which a very important point was the bifrequency. The bifrequency is a frequency of the lattice, a particular characteristic vibration frequency of the lattice. And that means that depending on the lattice, the frequency is higher or smaller, and the TC, which is directly proportional to the bifrequency, can change. But I wouldn't actually go further up because I don't know much more, but also it is a little complicated for just a general talk. But there are plenty of descriptions on the BCS theory, which is, it was really a little forgotten because the cuprates did not work. The theory doesn't explain the superconductivity in cuprates for reasons which are also complex, but then the hydrides do, as I've shown you. So, in fact, it is like a renaissance of the BCS theory, and the highest TCs obtained, certainly that under pressure, can be explained and actually predicted by the BCS theory.
Thank you so much. I think it's clear.
Pardon me?
I think it's clear. Okay. The last question.
Yes.
How does microstructure and particle size of the materials affect superconductivity? Is there any relationship with critical temperature?
You mean the structure of the material or the composition? Or what was
the microstructure or particle size?
Particle size in principle not. This is an atomic property. So we have actually worked with Maria Jose Torralbo and Veronica. We have done the influence of particle size and the critical temperature. And if you decrease very much this particle size, you do nanoparticles and very small nanoparticles, then TC disappears or decreases because, it's the mean free path decreases. And then so you finally end up with not having a superconductor. So you actually, the microstructure, if it's really very small, you can actually destroy superconductivity.
Okay, thank you.
Thank you so much.